Most people think floods happen because it rains too much. When rivers overflow, the explanation often stops there. But rainfall alone does not create the largest floods in history. In many cases, the real process begins far from cities and long before water reaches the streets. A flood is not a single moment of failure. It is the final stage of a system that has been filling, slowing, and reaching its limits over time. Rivers are not endless channels. They are physical systems shaped by gravity, terrain, and capacity, and those limits cannot be ignored. When those limits are exceeded, the outcome is not sudden or mysterious. It is the predictable result of water following the same rules it always has. A river is not just moving water. It is a system shaped by gravity, terrain, and time, designed to move a limited volume from land to sea. That volume is not infinite. Every river has a maximum capacity, determined by its width, depth, slope, and the speed at which water can flow downstream. When rainfall spreads across a wide drainage basin, water does not arrive all at once. It gathers gradually, flowing through soil, streams, and tributaries before reaching the main channel. As the ground becomes saturated, its ability to absorb water declines. At that point, nearly all additional rainfall becomes surface runoff, moving directly toward rivers instead of sinking into the land. This is when rivers begin to fill faster than they can release water. Once inflow exceeds outflow, the system starts storing water vertically, raising river levels toward their physical limits. River levels do not rise instantly. They increase over hours or days as water from upstream continues to arrive, even after rainfall has already stopped in some areas. Because large river systems drain vast regions, conditions far upstream matter more than what happens locally. A city can face flooding even under clear skies. Tributaries play a critical role in this process. When multiple branches peak at similar times, their combined flow can overwhelm the main river channel. This timing effect is known as flow synchronization. It determines whether a river absorbs incoming water safely or reaches capacity and begins to overflow. Once a river exceeds its banks, water spreads outward, slowing down and occupying floodplains that were formed by the same process over thousands of years. Floodplains are not accidental features. They exist because rivers have exceeded their banks repeatedly over long periods of geological time. Under normal conditions, these floodplains act as natural storage areas. They slow floodwaters down and reduce pressure on the main river channel. Problems arise when floodplains are altered or confined. When space for spreading water is reduced, river levels rise higher and faster than they otherwise would. Human structures do not create floods, but they can reshape how water behaves. Levees, embankments, and channels change the way rivers release excess volume. When rivers lose access to their natural floodplains, overflow does not disappear. It becomes more concentrated, more forceful, and harder to control. Large rivers respond slowly to change. Their size and inertia mean that once water levels begin to rise, reversing that process takes time. This delay creates a dangerous mismatch between cause and effect. By the time flooding appears downstream, the upstream system may already be fully loaded. Even if rainfall decreases, rivers continue receiving water stored across the basin. Soil, wetlands, and tributaries release that water gradually. This is why major floods often peak after the rain has ended. The system is still responding to what happened days earlier. At this stage, rivers are no longer reacting to weather. They are responding to accumulated volume, moving toward limits set by physics rather than forecasts. Because of this accumulation, flood severity is not determined by a single storm. It reflects how long water has been entering the system and how little space remains to release it. Large river floods are therefore slow disasters. They develop over time, often with clear physical warning signs that appear far upstream. By the time water reaches cities and towns, the system's response is already locked in. Local conditions can no longer change the outcome. This is why flood forecasting focuses on basins, not just clouds. The critical factor is how much water the system is already holding. When rivers overflow, it is not a sudden failure of weather. It is the final response of a system that has exceeded its physical limits. When these physical limits are reached, the outcome is no longer theoretical. Rivers respond the same way they always have, regardless of borders, cities, or human plans. History provides clear examples of what happens when large river systems exceed their capacity. One of the most studied cases occurred along the Mississippi River in the early 20th century. The flood of 1927 was not an anomaly caused by a single event. It was the result of a system pushed beyond its limits over time, following the same processes just described. The Mississippi River system drains one of the largest basins on Earth. By the 1920s, weeks of sustained rainfall had saturated soils across vast upstream regions. Water entered the system gradually through countless tributaries. As inflow continued, the river carried an increasing load long before flooding appeared downstream. Levees along the Mississippi were designed to confine the river within fixed channels. This reduced access to natural floodplains and forced more water to remain in the main flow. As river levels rose, pressure built along the levee system. Failures did not occur everywhere at once, but where accumulated stress exceeded structural limits. The resulting flooding reflected volume and timing, not a single storm. The system had surpassed its capacity, and the river responded according to physics rather than intent. As levees failed in multiple locations, floodwaters spread outward across low-lying areas. The river expanded beyond its confined channel and reclaimed space it had historically occupied. This expansion did not happen randomly. Water followed elevation, slope, and resistance, moving slowly but persistently across the floodplain. The scale of the flooding was amplified by the size of the Mississippi Basin itself. Water collected from distant regions arrived downstream over extended periods. What made the 1927 flood extreme was not speed, but duration. High water levels remained for weeks because the system could not release volume fast enough. When the river finally began to recede, it did so gradually. The system was emptying itself, returning to balance at the same slow pace at which it had filled. Events like the Mississippi flood are often treated as historical exceptions. In reality, they reveal patterns that appear repeatedly across different river systems. Large floods tend to occur not where rain is most intense, but where water accumulates over wide areas and long periods. This is why flood risk cannot be judged by local weather alone. The condition of the entire basin matters more than what happens in one location. When these patterns are misunderstood, floods appear random. When they are recognized, their behavior becomes easier to explain, though not always easier to manage. Floods are often described as acts of chaos. In reality, they are structured responses to physical limits being reached. Rivers do not overflow because they are unpredictable. They overflow when volume, time, and space align in ways the system can no longer contain. The Mississippi flood of 1927 was not a failure of nature. It was a reminder of how large river systems behave when their limits are exceeded. Across the world, different rivers follow different paths, but the rules that govern them remain the same. When rivers overflow, they are not breaking those rules. They are obeying them exactly as they always have.